Hello everyone, and welcome to some more remote learning. Today we're going to go over the length of curves. We can easily figure out how far a curve goes by subtracting the starting point value from that ending point value, whether we want to know how far it goes in the x or whether we want to know how far it goes in the y. But what if we want to know the total distance of that curve or the actual length of the curve? So I think a good way to think about this is if you think about throwing a ball, it's going to have sometimes like some sort of curve. Most of the time we care about how far the ball was actually thrown. But what if you want to know how far the ball traveled over the course of being thrown? That's going to be that length of that curve. So in this video, we're going to talk about actually figuring out that total length. Now the proof for this is pretty neat, and it's all based on the Pythagorean theorem, where we have a change in y and a change in x. But for now, I'm going to write down the formulas, and we'll kind of get a little into that in example 1, but I'll save that more in-depth explanation for your lesson. So the arc length for y equals f of x. Well, if we want to know an arc length, like I said, it's going to be based on the change in y and the change in x. And the formula goes from a to b, the square root of 1 plus f prime of x squared dx. Now for this formula, we need to know the derivative of f of x. And in order to integrate that, that derivative needs to be continuous from a to b. So from the point a, f of a, all the way to the point b, f of b, the derivative needs to be continuous in order for this definition to hold true. Now, let's do this not with respect to x, but let's talk about it with respect to y. The same concept, except now I'll go from some point c to d. So this is going to be g of c, comma c as my starting value, and g of d, comma d as my ending value, because that input will give me my x, and then that output is just what I'm plugging in for y. So these c's and d's are my y values of that coordinate. And then we're going to have the square root of 1 plus g prime of y squared dy. So again, the derivative needs to be continuous from c to d. So let's go ahead and jump into example 1. In example 1, it asks us to find the arc length of y equals 2x plus 1 on the interval from 0 to 4. So let's think about what y equals 2x plus 1 looks like. Well, y equals 2x plus 1, we have a y-intercept of 1, and that ending value, if we were to plug in 4 times 2 is 8, plus 1 is 9, so then we'll be at 4 in the x and 9 in the y. So here's the point 4, 9. That y-intercept, where we're starting our interval at as well, is 0, 1. It's a linear equation, so it's just a straight line. I can easily find that distance using the Pythagorean theorem. So we have some change in x, and then some change in y. My change in x, well, to go from 0 to 4, that's a change of 4, and to go from 1 to 9, 9 minus 1, that's a change of 8. So let's do the Pythagorean theorem. This side length is going to be 4 squared plus 8 squared and the square root of that. So what is the square root of 4 squared plus 8 squared? 4 squared is 16 and 8 squared is 64. Adding those together, 64 plus 16 is going to give me the square root of 80. And 80 is equal to 16 times 5. So writing that with a perfect square inside, I'll simplify this down to be the 4 square root of 5 as the length of that curve, which, because it was linear, it was fairly easy to do without using any formulas. But let's go ahead and do the arc length formula for y equals f of x. So using our formula, we need to find the derivative and square it. So if y equals 2x plus 1, y prime, or f prime of x, is equal to 2. So that means when I square that, y prime squared is going to be equal to 4, because 2 squared is 4. So plugging this into the formula, we're going from a to b, so our starting x value is 0, and our ending x value is 4. So the lower bound is 0 to 4, and then we have the square root of 1 plus, we already did a little bookkeeping, we know what f prime of x squared is, that's our y prime squared, which is 4, and we're integrating this with respect to x. So this simplifies down, the square root of 1 plus 4 is the square root of 5, and we're integrating that with respect to x. So we get the square root of 5 times x from our bounds 0 to 4. All we need to do is plug in 4 and subtract plugging in 0. So 4 times the square root of 5 minus 0 times the square root of 5 is just going to be 4 square root of 5. So you can see, using that formula, we get the same exact value by using that Pythagorean theorem. Now, either way will work when we have a straight line, but we won't be able to do the same thing if we had some sort of curve. We're not going to be able to get that perfect right triangle. So from here on out, let's make sure we're using that formula. So moving on to example 2, we're going to find the arc length of y equals x to the 2/3 on the interval from 0 to 27. So y equaling x to the 2/3, y is pretty much interchangeable with f of x because y is some function of x. I can write this as f of x equals x to the 2/3 if you're more comfortable seeing it in function notation. What we need to do though is we need to find f prime of x because that's used in our definition to find that arc length. So I'll take the 2/3, bring that down in front, and then decrease that exponent by 1. So 2/3 x to the negative 1/3. I'm going to rewrite this so I don't have a negative exponent. That will give me 2 over 3x to the 1/3. Now, one of the conditions for being able to use this formula was what? That our derivative had to be continuous along the entire interval. So we need to ask ourselves, can we indeed plug in all of those points within our interval? What would make this undefined? Well, if x was 0, the derivative would be undefined. And do we have 0? Yes, we do. So we cannot find the arc length with respect to x. But that doesn't mean we can't find the arc length at all. Let's try it with respect to y. So solving for x so that we have a function in terms of y, I'm going to raise both sides of my equation to the 3/2. So that's going to leave me with x equals y to the 3/2. So some function of y equals y to the 3/2. So I'm just going to say g of y equals y to the 3/2. You could leave it in terms of x. G and y and x are representing that same function. I'm just writing it in function notation. So now I need to find that derivative. G prime of y, the derivative, x prime, it is going to be bringing that 3/2 down in front and decreasing that exponent by 1. 3/2 times y to the 1/2, or 3/2 square root of y. Now we need to ask ourselves, are we continuous on the interval? But this is no longer our interval because these were for x. This was like our a and b, when we really need to find our c and our d. But if we know the bounds for x, we can easily plug those in and figure out our bounds for y. So I'm going to plug 0 into our original, and I'm going to plug 27 into our function and solve for y. That will give me my y bounds. So my new interval, plugging 0 in, I'll have 0 to the 2/3, and then plugging 27 in, I'll have 27 to the 2/3 as my bounds for y. 0 to the 2/3 is going to be 0, and 27 to the 2/3, taking the cube root of 27 is 3, and then squaring that gives us 9. So our bounds are from 0 to 9. And we need to ask ourselves, when is g prime of y not continuous? That's when we have negative numbers, because we can't take the square root of a negative without it being imaginary. So looking at this, we don't have any negative numbers in our interval, so we know that we are indeed continuous along our derivative. And just to do a little bit of bookkeeping so that we don't have to square it within our formula, I'll go ahead and square our derivative now as well. So g prime of y squared is going to be 3/2 squared, which is 9/4, times the square root of y squared, which is y. Now plugging everything into our formula, we're going from our new bounds in terms of y, 0 to 9, times the square root of 1 plus g prime of y squared, which is 9/4 y, and integrating that with respect to y. In order to integrate this, how are we going to do it? With a little bit of u substitution. So we'll set u equal to 1 plus 9/4 y, then du, taking the derivative, would be 9/4 dy. So setting up my new integral, I'm going to go from, well, here's the thing with u substitution. We can either switch our bounds now so that it's in terms of u, or we can leave our bounds as in, making sure after we integrate, we plug y back in. What I'm going to do is just switch my bounds because it's fairly easy. If I plug in 0 for y, what is my u value? My u value would be 1, because 1 plus 9/4 times 0 is 1. And if I plugged in 9 for y, well, I'm going to have 1 plus 9/4 times 9, which would be 1 plus 81/4. I can simplify this down, combining with a common denominator. 1 is the same as 4/4. So this is really going to be 85/4 that I'm plugging in. So now that I have my bounds in terms of u, I don't ever need to switch back to y. I'll finish out solving this problem with respect to u. Remember, 1 plus 9/4 y was u. So I'm going to have the square root of u, or I can write this as u to the 1/2, because it might be easier to see that as an exponent when we go to integrate. And dy, well, I know that du is equal to 9/4 dy, which means that dy itself is equal to 4/9 du. So I'll bring 4/9 out in front, du. Again, all I did, I saw here that I did not have a 9/4 somewhere in here to make du, so I had to divide by that 9/4, so multiply by 4/9. So let's go ahead and integrate. U to the 1/2, I'll raise that exponent by 1 and then divide by the new exponent. So this is going to give me u to the 3/2 divided by 3/2 will be 2/3 u to the 3/2, but I have that 4/9 out in front, so I'll multiply that in. And I'm going to evaluate this from 1 to 85/4. Simplifying to make this a little bit easier, 4 times 2 is 8, so I'll have 8u to the 3/2 all over 9 times 3, which is 27. And I'm evaluating this from my bounds of 1 to 85/4. So let's go ahead, plug in 85/4 and subtract plugging in 1. So 8 times 85/4 raised to the 3/2 all over 27. I'll subtract 8 times 1 to the 3/2 all over 27. Now I can do a little bit of simplification here, but this problem looks a little messy. What I'm going to do is I'm going to split this fraction up because I know that the square root of 4 is 2 and 2 cubed is 8. So what I'll get is 8 times 85 to the 3/2 all over 8, and that is all over 27, minus 1 to the 3/2 is 1, so this is just going to be minus 8/27. Now you can see that my 8 divided by 8 will cancel out to equal 1. So I have 85 to the 3/2 over 27 minus 8/27. So this is going to be 85 to the 3/2 minus 8 all over 27. Now, I wouldn't expect you to be able to simplify this down any further without a calculator, so I'll leave this as is. 85 to the 3/2 minus 8 all over 27 is the length of that curve, which, if we plugged it into a calculator, this would be rounded to the nearest whole number, about 29. Let's continue on to the last example in this worksheet. For example number 3, we're going to find the arc length of the curve y equals x to the 4th over 4 plus 1 over 8x squared from x equals 1 to x equals 2. So the first thing we're going to check is our derivative continuous along our interval? In order to do that, we need to take the derivative. So y prime, or f prime of x, is going to equal taking the derivative of x to the 4th over 4. That's going to be x cubed, because when we bring that 4 down in front and subtract 1, 4 over 4 times x to the 3rd is x to the 3rd, plus taking the derivative of 1 over 8x squared, pulling that 1/8 out in front, this x squared is like x to the negative 2. So taking the derivative of x to the negative 2, bringing that negative 2 down in front and decreasing that exponent by 1, that's going to be negative 2x to the negative 3, or negative 2 over x cubed. And remember, that all is multiplied by this 1/8. So negative 2 over 8 is actually going to be a negative 1/4. And so I'll have minus 1/4 x to the negative 3, or minus 1 over 4x cubed. The only thing that would make this function undefined is if x was 0 and my interval goes from 1 to 2. 0 is not included in that interval, so I can indeed complete the arc length formula. So I'm going to go from 1 to 2 of the square root of 1 plus f prime of x squared. I like to do a little bit of bookkeeping first in order to make it easier to do. So as opposed to squaring it within my definition, I'm going to square it over here. So f prime of x squared. So I'm going to take that x cubed minus 1 over 4x cubed and multiply it by x cubed minus 1 over 4x cubed. I'm going to write it up here, these two binomials, so you can see me foiling it out. X cubed times x cubed, adding those exponents, will be x to the 6th. Then we'll have x cubed times negative 1 over 4x cubed, which the x cubed will cancel out to give me negative 1/4. And that same thing's going to occur for those inner terms. Negative 1/4 plus negative 1/4 is a negative 1/2. And then I'll be adding, because these two are negative, and when they get multiplied together, that's going to be 1 over 4 times 4 is 16, and x cubed times x cubed is x to the 6th. So I'll go ahead and plug this in for my f prime of x squared when using my formula. X to the 6th minus 1/2 plus 1/16 x to the 6th. And this is all integrated with respect to x. Now, I can't integrate this with my current integration techniques, so I'm going to see if I can do some algebraic manipulation, simplify down, and solve. So I can combine 1 and negative 1/2 to give me 1/2. So I'll have x to the 6th plus 1 over 16x to the 6th plus 1/2. Now, with these arc length problems and our current knowledge of integration, there's only going to be so many ways that we're going to be able to integrate this without technology. One would be if what we saw was the derivative of a trig function. One way would be by completing the square, factoring, u substitution, maybe if it was a nice trig function. So example 1, we were able to just straight up integrate. Example 2, we had to do some u sub. And in example 3, this is actually a perfect square. So when I take the square root of a perfect square, I'll be able to integrate that. If you can see, x to the 6th plus 1 over 16x to the 6th plus 1/2 is, well, I need to have x cubed and x cubed, because x cubed times x cubed is what gives me that highest power of x to the 6th. what I need to figure out is how I can either multiply to get 1/2 and add to get 1 over 16x to the 6th, or vice versa, multiply to get this and add to get 1/2. So in order to multiply to give me 1/2, that would need to be a 1 over square root of 2 and a 1 over square root of 2. If this was a perfect square, I need everything to match. And in this case, well, when I go to FOIL that out, I definitely don't get that. So let's look at that 1 over 16x to the 6th. This 1 over 16x to the 6th, in order to have two of the same thing that multiply together to give me that, that's going to be 1 over 4x cubed. So if I add 1 over 4x cubed to both, FOILing that out, you'll see I'll get x to the 6th. There, my last terms is indeed my 1 over 16x to the 6th. And then if you look at x cubed times 1 over 4x cubed, that's 1/4. And then I'm adding that to x cubed times 1 over 4x cubed, which again is 1/4. And 1/4 times 1/4 is indeed 1/2. So what's underneath my radical is equivalent to, writing this out, square root of x cubed plus 1 over 4x cubed squared, because this was my perfect square. And if you need help figuring out perfect squares, I have a bunch of worksheet videos that I've done going through more in depth explaining this process. But for now, I knew that this had to be a perfect square in order to integrate with my current integration strategies, knowing that I didn't have to use technology on this worksheet since I created it. So I was able to pick my different factors apart to find that perfect square. Now the square root of x cubed plus 1 over 4x cubed squared, with respect to x, that's going to simplify down to the integral from 1 to 2 of x cubed plus 1 over 4x cubed, since the square root and the squared will cancel out. And I need to just integrate this with respect to x, plug in my bounds, and solve. So doing that quickly, x cubed when integrated becomes x to the 4th over 4, and then integrating 1 over 4x cubed, that's like integrating 1/4 times x to the -3. So adding 1 to that exponent will give me a -2, and then dividing by a -2, that's going to be 1/4 times x to the -2 all over -2, which I'll be subtracting 1 over 8x squared. And I'll evaluate this from 1 to 2. So plugging 2 in, 2 to the 4th is 16. 16 over 4 is 4, minus 1 over 8 times 2 squared, that's minus 1 over 32, because 8 times 4 is 32. So that's what I get when I plug 2 in. Now when I plug 1 in, I'll subtract that. So that's going to be 1/4 minus 1/8. Simplifying this down, I'll find a common denominator between 4 and 32, which is going to be that common denominator of 32. So 4 times 32 is going to give me 128. So I'll have 128 over 32 minus 1 over 32, which simplifies down to 127 over 32. And then I'll be subtracting 1/4 minus 1/8 is going to be 1/8, because that's like 2/8 minus 1/8, which is 1/8. So now, taking 127 over 32 and subtracting 1/8, 1/8 I can think of as 4 32nds. So 127 minus 4 is going to be 123, and that's all over 32. That's the length of my curve in example 3. So again, where you're at in your studies, if you're told to find the arc length without using technology, it's going to be a little bit of algebraic manipulation in order to get there, or it's going to be something that you can easily integrate, like a u sub or something that evaluates to a trig function. Now the neat thing about arc length is we're going to continue on with this arc length and now use it to find surface area. So kind of like how we used area, we did a simple lesson on that and then learned how to find volume. we're taking this arc length and we're expanding it to find the surface area. So continue on to the next video where I'll do some example practice problems, but don't forget the square root of 1 plus the derivative of your function squared, because that's going to come into play in our integral. But until the next video, good luck with your online learning.